Welcome to the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops into your brain, just write it down. I will gather a bunch of them up and I will answer them here. Now, of course, I record this question show live every Monday at 5 p.m. Pacific on my YouTube channel. So if you want to ask a question to me live, which is great because then we get that back and forth. If you have any other follow-up questions, then you can do that. Just there'll be lots and lots of events in my calendar. You can just pick one and join. But also, I gather a bunch of the questions that have been asked over the last question shows and anywhere across my channel and cover those as well. So come join me Mondays at 5 p.m. if you want the live version of the experience. All right, let's get into this week's questions. Wintermute. Do pulsars ever slow down? Yeah, pulsars slow down. So for those who don't know what a pulsar is, when a star with 8+ times the mass of the sun explodes as a supernova, the outer layers all collapse inward and the force creates a neutron star where all of the electrons and the protons are smushed together. I believe that's the scientific term. And the thing is entirely made of neutrons. When a neutron star first forms, it has all of the rotational velocity, momentum of the original object. But before, it was this giant star. And so it conserves all of this momentum down into this small object. And of course, you've probably heard about the idea of the ice skater pulling in their arms to go faster. And so same situation. All of that mass is now compressed into a much smaller area. And so this thing is rotating insanely fast. When it first is formed, it can rotate hundreds of times a second. And in fact, astronomers can tell how old a pulsar is by how fast it's spinning, because a pulsar does slow down its speed of rotation. And what happens, and this is the part that's kind of amazing, because you're wondering, like, what can slow it down? I mean, it's just turning, it's in the vacuum of space, nothing is acting against it, so it should just be able to just turn and turn at the same speed forever, and yet they do slow down. And so what's slowing them down is that they are emanating gravitational waves. They are essentially releasing gravitational energy, and as they do this, it has to take away from something, and it takes away from the speed of the rotation. And so when we see different kinds of neutron stars out there, pulsars, neutron stars, magnetars, they're all flavors of the same thing. It's just that when these pulsars are brand new, when these neutron stars are brand new, when they're newly formed, they're rotating very quickly. And of course, when they're rotating very quickly, you get these really powerful magnetic forces that sort of wrap around the star and channel with the magnetic fields radio emissions that come out kind of like a lighthouse. And so astronomers are able to measure the speed of the star's rotation by how fast these light beams or radio beams are passing our point of view. So it's kind of amazing that pulsars do actually slow down, even though it's seemingly no force is acting upon them. S.E. Sander. What is it with scientists using the word in situ every chance they get? They squeeze it into the acronym of damn near every single object built by NASA. Lol. In situ actually, I mean, I hadn't heard it a lot before the last, say, 10 years, 5 years. I mean, there's some people who have been using it before. And in situ is a Latin term. It just means on site. And what it means is that you are going to try to produce whatever you need, be it atmosphere, be it rocket fuel, be it construction material, from the location where you are. And of course, in the past, if you go hiking, and you're going to build a fire. You're going to make the fire in situ. You're going to find firewood around the campsite, and you're going to build a campfire. You're going to have water is going to be in situ. You're going to find a pond. You're going to find a lake. You're going to get your water from there. Other stuff you're going to have to bring with you. You're going to bring your tent, your sleeping bag, etc. And so with exploration, the more you can gather your materials on site, like build your moon base out of moon regolith or build your rocket fuel on the surface of Mars, the better. Why do they use the term? Well, why do scientists use any term? It's a precise term. Generally, scientists prefer to use terms which are very precise, that when you use the term, you know exactly what it means. And so in this case, I mean, yeah, you could use a bunch of other terms. You could say you're living off the land, or locally sourced, or, locally grown. But in situ provides exactly the term that people need to know, which is that you're going to make your rocket fuel from the surface of Mars. You're going to make your building material from the surface of the asteroid. And so in situ is a great term. So get used to it. Adam Stump. Hey Fraser, what are your thoughts on the search for life comparing Europa to Enceladus? Do you think that Enceladus has more possibilities due to the vents and relatively thin ice crust? Are there any missions planned in the next decade to land on either moon? Both Europa and Enceladus are kind of amazing places for us to continue the search for life, and they both have their advantages and their disadvantages. So Europa is one of the moons of Jupiter, which means that it's way closer. It takes only, like, say, 3 years to send a spacecraft to Europa. And so if you learn anything, you want to send a follow-up mission, it's a lot quicker. But the problem is that Europa's water ice is a little more elusive. Although it appears there are geysers on Europa, we're not entirely sure, and we're not sure what kinds of materials, how easy it's going to be able to investigate them and be able to answer some of these deep questions about whether or not there's life under the ice, or what kind of conditions are under the ice on Europa. Enceladus seems like a much better world. You've got these tiger stripes on the south pole of the moon, and it is blasting water ice out into space. And in fact, Cassini was able to look at these geysers so well that it was able to detect that there's hydrogen gas dissolved into the water underneath Enceladus. And hydrogen gas is like the perfect food for microbes. But getting to Saturn is far. You're looking at 5 years plus to be able to send a mission, depending on how many flybys you're going to need to do. So you're looking at a very long journey to get out to Saturn. Which one do you send? Both, obviously. If I had to choose, I think I'd go with Europa because it's closer, because it's bigger, because it clearly has a very interesting history on the surface. There are hints that the geysers are there, and when the Europa Clipper or the JUICE mission arrives at Europa, they'll be able to peer into these geysers and get a better sense of what's going on. So I think that once there's analysis of Europa that's as good as the analysis that Cassini did, then Europa will look as good as Enceladus. But if it turns out there's no geysers at Europa, then Enceladus is going to be the better one. Whichever one is vomiting its ice and nutrients out into space is the one you want to go and visit. Jeff Sonderman. Would Starship with orbital refueling be capable of direct missions to planets farther than Mars? Could it visit Jupiter, Saturn, and go into orbit there? Yeah, as I understand correctly, if you can refuel a Starship in orbit, you can pretty much go anywhere you want in the solar system and go into orbit. You could go to Pluto with a Starship, and you could do a direct flight. So you wouldn't need to necessarily make all of those flybys, those gravitational slingshots, like what Cassini did, what New Horizons did to be able to get out to Pluto using a slingshot of Jupiter. You could do a direct shot, the most direct, the fastest flight you could do. And then it would just be a matter of like, how quickly do you want to burn through all of the fuel that's in the Starship? But I don't know of anyone doing any calculations. Like if you had a fully refueled Starship in orbit around the Earth, and then you wanted to fly and put a spacecraft into orbit around Jupiter as quickly as possible, what would be the most direct flight? How quickly could you do it? My guess is you could shave huge chunks of time off what is currently done. Because right now, when you launch, say, a mission to Jupiter, you're launching some rocket, say an Atlas or a Delta. You've got a upper stage, you've got a kick stage that's going to give the spacecraft the final little kick of velocity, and then it's going to have some rockets on board so that it can go into orbit. But if you've got Starship, a fully fueled Starship, I mean, that thing could take off and go into orbit just from the surface of the Earth. So it's a phenomenal amount of energy that's going to give you delta V. But I haven't seen anyone who's actually done like specific calculations. But yeah, you could go anywhere you wanted in the solar system. Phil Deshane. Hey Fraser, would it be possible for planets to have an orbital resonance the same way that Jupiter's moons do? Sure, yeah. In fact, astronomers are pretty certain that there are many exoplanetary systems out there that the planets are in some kind of orbital resonance with each other. And really, it comes down to how close they are together and how much they're interacting. Because it's sort of like if the planets can't get along, then they're going to collide with each other, or they're going to kick each other out into space, or they're going to get crashed into the star itself. But they can set up this orbital resonance where they're able to interact with one another in a way that is perfectly balanced, essentially forever. And before Pluto was unplaneted, we actually had a case of an orbital resonance here in the solar system between Neptune and Pluto. I forget the exact number, but essentially Neptune and Pluto can never crash into each other because they are in an orbital resonance with each other. I think it's a 3-2. Anyway, and so, yeah. In fact, many of the planetary systems that have been found out there have been found in various orbital resonances. It's a very common thing in the universe. Sunny Vegas. Is fusion a possible solution for space travel? In theory, fusion would be a wonderful way to do space travel, a very powerful form of propellant. The problem is that we can't even do fusion here on Earth. There's always this classic joke that we're always 30 years away from fusion. Now, you could set off a fusion bomb, and it would, I guess, send parts of your spacecraft in some direction. But yeah, you want to be able to have controlled fusion. And that has still just been beyond our reach. There are some huge experiments that are going on right now. The best example is called ITER, ITER. And it's this giant experiment that's going to be going on in Europe. And it's going to be like the first attempt to develop a sustainable fusion reaction. There's other experiments. I know that China is doing them. There's one in Germany. I think Lockheed Martin has an attempt on a fusion experiment. So I think we're going to see somebody crack fusion in the next couple of decades. Hopefully it won't be 30 years. I've also seen some interesting ideas for sort of fusion adjacent drives that could be developed more quickly. And there's one idea, and we've mentioned it a couple of times in some of our episodes, just about this idea of a fusion drive that could carry a spacecraft out to, say, the orbit of Pluto in just a couple of years, as opposed to 10 years. So, in fact, NASA awarded a NIAC grant to one of these. So I think the conservative answer is we're going to see controlled fusion happen here on Earth. Then we're going to see miniaturization of controlled fusion, what is the smallest possible fusion system that you can have. And then we're going to see space-based miniaturized controlled fusion. But each one of those, you're going to need to add 30 to 50 years. So I would be surprised if we see fusion drives before the end of the century, would be my guess. There's a lot of technical issues to be sorted out first. Everything's harder in space. Wince Gargantuan, what are the plans for colonizing the universe? There are no plans for colonizing the universe. If you were to run a thought experiment, what does the future of humanity look like if we just continue to increase our ability to generate energy, and then you match that against the amount of work it's going to take to be able to fly to another star system, you would anticipate that we'll start to have the technology to be able to do that in about 700 years. So in about 700 years, we'll be able to start sending spacecraft at about 10% the speed of light to other star systems. And then once you get to another star system, then you would want to build some kind of robot factory in that star system. And then you'd want to send robots to other star systems. But then that would just be robots. So if you're talking about colonization, then you're going to want to send living creatures. So maybe you would send some kind of gene factory to the next star system, and then while the robot factory is pumping out robots that are going to go to other star systems, you've got the gene factory, which is seeding the planet, terraforming the planet and seeding it with life, and then also providing genetic material to the robots that are then going to other star systems. Estimates have said that if you did that, it would take you somewhere around 1 to 10 million years to fully colonize the entire Milky Way. So you would have inhabitants in every star system in the entire galaxy. So 10 million years? That's the plan? 10 million years. We'll check back and see how that's going. Mr. Kropkin, how many years is a close enough flyby of a star to make a starhop more possible? I wonder if this is a question based on a recent interview that I did. This idea that stars actually pass close to the solar system on a fairly regular basis. And so right now, yeah, if you wanted to send a mission to Alpha Centauri, it would take you tens of thousands of years. Maybe you could speed it up, but you're still going to have to travel 4.5 light years to get to the nearest star. But if you just wait 1 million years or so, and I think that's the number, it's about 1 million years, then stars will make very close flybys. In some cases, tens of thousands of astronomical units, like well within the Oort cloud of the solar system, close enough that they can influence the solar system a little bit with their gravity. And then you can use a fraction of the energy to be able to reach these other stars, and then wait for those stars to get close to other stars and use a fraction of the energy. And it doesn't actually add a lot to the time that it would take to be able to go to another star system. And so when you sort of think about that, it's kind of fascinating that if we can be patient and just wait 1 million years or so, then it gets a lot easier. So either we go the hard way right now and just like overbuild our rocket system and just brute force our way to another star, or we just wait patiently and eventually orbits will line up and we'll be able to just jump to another star system. And you can imagine, like, once we can start to detect rogue planets, they come probably even closer. Brown dwarfs probably come by all the time. Once we have a really good survey of everything that's around us, I'll bet you those numbers will come way down. And then it's just a matter of star hopping from object to object across the entire Milky Way. So you could probably cut those estimates down significantly. Arjun, why is the Drake equation always used to try and predict the likelihood of aliens? No one came up with another equation in all these years. I think people use the Drake equation because it's famous, not because it's necessarily the best equation. For those who don't know, Drake put together this, I think it's like there's 6 variables. And when you, like, what is the number of stars that have planets? What are the number of planets that are habitable? What are the number of planets that develop life, etc.? And it's sort of an exercise to show you that even if you choose fairly conservative numbers for all of these parts, you end up with a fairly large number for the number of intelligent civilizations that could be in the Milky Way. But obviously you could make it more difficult. You say, what are the number that have large moons that protect them, stabilize their climate, and what are the number that have a star that doesn't produce deadly flares, and et cetera, et cetera. You could kind of go on forever. And it also just sort of showcases the reality that we have no idea, that the Drake equation really falls apart as you get halfway through of it. The second you ask yourself, what percentage of planets will form life? The answer is we don't know. We have no idea. We have a sample size of 1. We have never found another place that has produced life. And so far, until we've like really well scoured all of the other places in the solar system, the answer is 100% of planets form life. So therefore, there's 100%. What percentage of planets that form life go on to develop intelligent life? 100%. Right? And that's ridiculous. Probably, maybe. So if you actually like take that number and try to extrapolate any useful data, it all just falls apart. And that's the real problem with the Drake equation, is it does not allow you to make any meaningful estimate for the number of civilizations, of intelligent civilizations that are in the universe, because there are just too many variables that we have zero data for. But the thing that's interesting is it does give you a bit of a goal. Like if you looked at the Drake equation 50 years ago, no part of the equation was solved. But now we know roughly what percentage of stars out there have planets. It's amazing. We roughly know what percentage of the stars that do have planets in the habitable zone. We roughly know some of the sizes of the different kinds of planets that are out there. And so it's kind of fun if you make this list and you sort of work your way through all the variables as you work your way from left to right, trying to sort out how many civilizations there are in the universe. But really, until we've had a chance to observe other planetary systems comprehensively to know if there's life there, we won't be able to extrapolate to figure out how many civilizations there are in the Milky Way. So there could be 0 and there could be 400 billion, and it's somewhere in between 0 and 400 billion. 6 Bob Ohms. Just me, or do nuclear thermal rockets seem so much better than chemical and ion engines for Mars or Jupiter missions? Different propulsion systems have their value. Like a chemical, like why do we like a chemical rocket? Why have we not moved from a chemical rocket to a nuclear thermal rocket? Nuclear thermal rocket can produce a thrust that's faster, more powerful than a chemical rocket, but you are attempting to launch a nuclear reactor from the surface of the Earth out into space. When you see the kind of concerns that people have for nuclear reactors just in general, the ones that are relatively safe, housed in concrete here on Earth, and what do you do with the nuclear waste, you can see why people are a little bit concerned that you would put one of these things on something that can explode from time to time, throwing all of the debris all over the landscape and poisoning the environment. So you can see why people are loath to consider launching them from Earth. Chemical rockets are the way right now, and you can't use an ion engine to launch from Earth. Once you're out in space, sure, that makes more sense that you could have some kind of nuclear thermal rocket that's in orbit. But how did you get it into orbit? You had to launch it from the ground. So again, you've got some risk. Use a nice, safe chemical rocket. You launch it into space. Now it's in orbit. Then you turn it on, and it thrusts to carry your spacecraft to Mars or Jupiter or whatever and beyond. Sure. But then you got a lot of moving parts. It's sort of simple to just take a big rocket, just launch on a direct trajectory to Mars or Jupiter or wherever you're trying to go, and then the payload is on its way. And so while in theory, a nuclear thermal rocket can provide more efficiency, it doesn't really make sense anymore. And especially when you look at things like some of the like orbital refueling and two-stage fully reusable rockets. At this point, we're bringing the rocket cost down by orders of magnitude, that the cost is really just a tank of fuel. Could you build a nuclear powered airplane? Sure, you probably could. I'm sure somebody has. I'm sure somebody's going to link in the chat that somebody has done this. But the point is that it makes more sense to use airplane fuel because it's cheaper. And so when rockets were really, really expensive and getting Delta V was really, really hard to do, then they were a lot more accessible. I think all of the nuclear reactors that are going to be developed, they're going to be used for space, are going to be used for power generation in places where power is hard to get. So in the shadowed craters on the moon, on Mars where it's hard to set up enough solar panels, out at Jupiter. Then you put a nuclear reactor on your spacecraft, use that to power an ion engine. That's a really great way to be able to efficiently use the electricity that's coming out of a nuclear reactor. So I don't think we will ever see nuclear thermal rockets be used in the way that you're hoping. I think we're at a point now where chemical rockets are just coming down. Again, in situ, which we talked about earlier in the episode, you can go and land on an asteroid. You can extract water. You can create more rocket fuel, and away you go. You can't land on an asteroid and process uranium to be able to produce more rocket fuel. So I just think that in terms of sort of cost and sustainability, I think chemical rockets are going to be with us for a long time. Some mix of chemical rockets and ion engines, which are incredibly efficient and can speed up a rocket over long periods of time. But we'll see what the future holds. I know that NASA has been instructed to put in more development of nuclear thermal rockets, so we might see their development in the future or continued development in the future. But I don't think they're going to last. I don't think we're going to see a lot of them into the long term, even if they're more efficient, faster, etc. More questions in a second, but first I'd like to thank our patrons, DS, Eric Mowry, Robert Wenger, Doug Heedy, Chuck Haberlein, Burnett Nicholson, and the rest of our 836 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universe today. Purple. I'm thinking of buying binoculars to look at the night sky. Would I see the moon well? What specs would work? Good choice. Binoculars for seeing the night sky. I highly recommend it. I've got a pair of Celestron 15x75 Skymasters, and they're terrific. I really like them. You can use like just regular bird binoculars or just whatever binoculars you want. And I would recommend just like starting there. If you're wanting to see the moon well, I would say no. I mean, looking at the moon through a pair of binoculars looks better than looking at the moon with your own eyes. But it really doesn't match how well it looks at looking at the moon through a telescope. That there's a magnification, there's a size there that makes the moon look really amazing. And so if you're wanting to do more planetary and lunar stuff, I would recommend making the jump to getting like a Dobsonian telescope. But if you just want to be able to go out and, you can see comets with binoculars. You can see the moon. You can see the Milky Way. You can see some of the really interesting objects that are in the night sky. I mean, you can see globular clusters. You can see galaxies. You can see nebulae. All these things, especially if you have dark skies. Binoculars are great. And the thing I really like about binoculars is they get you really comfortable just learning your way around the night sky. So like the first step is just being able to find things. Like, can you orient yourself? Can you find your way across, jumping from star to star to be able to find specific objects that you know are there? You can't see them with your regular eyes, but once you use the binoculars, you can see them. And also sort of having two lenses at the same time. There's something special about using both of your eyes at the same time. And so the perfect setup is to have like a Dobsonian telescope, like a 6-inch or an 8-inch Dobsonian telescope. They're very fast to use, and they pair really nicely with a pair of binoculars. They're relatively inexpensive. You can buy a 6-inch Dobsonian for a little over $200. You can buy an 8-inch Dobsonian for about $350, and that's the size that I recommend. You can build your own. There's lots of plans for building your own Dobsonian telescope on the internet, and you can do it then for about $50. And it's my favorite kind of telescope. Even though I have another telescope behind me, Dobsonians are the greatest because they're just so fast and easy to use. So definitely get a pair of binoculars if your budget is $50 to $75. Start there, and if you want to take it to the next level, then get a Dobsonian telescope as well. But don't go bigger than 8 inches. That is beyond that. They're way too expensive, and they don't deliver a lot of improvement in what you can see. Raphael Domenichini, how close are the stars to each other within a star cluster? It depends on the star cluster, but on average, stars in the Milky Way are about 4 light years apart, sort of the distance from us to Alpha Centauri. And that includes not just the bright stars, but also the dim stars. I mean, red dwarf stars as well. The night sky that we see here today is what you'd see anywhere. But if you're in a globular star cluster, then the average distance from the stars is about 1 light year apart. And so you're going to see a vastly different night sky if you were in one of those clusters. It wouldn't be like daylight, but you would definitely see just a sky completely filled with stars. And there's a lot of stars. I mean, a single globular cluster can have hundreds of thousands of stars inside of it. And so it would be kind of a mind-bending experience. Then, I mean, if you were in something like, say, I don't know, Pleiades or something, then there would be a bunch of bright stars all around you, but not the same as like a globular star cluster. But yeah, it would be amazing. I think, people always ask me, like, where would you like to go in the universe? And the problem is that it hasn't been surveyed enough for me to be able to give you an answer. But I would definitely want to be standing on a planet inside a globular star cluster and to be able to see all of the stars around. That would be amazing. Matthew Jones. Fraser, previously Elon Musk suggested nuking the poles of Mars. Wouldn't it be more practical to push comets or broken up ice pieces towards the poles instead? So here's the problem. If you nuked Mars, then you would, if you're trying to have a civilization that's going to be able to live on Mars and you nuke the planet, you're making the planet uninhabitable for a very long period of time. If you crash a comet into Mars, you're going to make a planet that is a mess for a long time. I mean, you're going to be filling the sky with material. You're going to be raining debris. It's going to be bad. So, and if you hit it with something like really big, then you're going to do a lot of damage. Like if you hit it with something big enough to maybe add mass to Mars, you're going to be making the planet molten again, which is bad for habitability. And so I think if you did want to terraform Mars, which I am not super convinced is the kind of thing that we'll be able to take on within the next few thousand years, your best bet is slow and steady wins the race. The reason why Mars is losing its atmosphere is because of the solar wind. And so if you can actually block the sun's solar wind, if you can put some kind of structure at the Mars-Sun L1 Lagrange point, you will block the solar wind. And so then that will stop pushing away the gases from Mars's atmosphere. And there's actually just like volcanic outgassing that's happening all the time on Mars. And that would just build up in the atmosphere to the point that Mars's atmosphere would thicken to the point that water would start to melt on the surface of Mars. And so you could actually gently, carefully make the conditions on Mars better. But to get Mars to a place where it's as good as the Earth is beyond our understanding of geoengineering at this point. And so when you are attempting to take on these enormous scale activities, it's best to move carefully, work slowly before you attempt to just smash comets, detonate nuclear weapons on the surface of Mars. So that would be my recommendation. Richard L. Mars rover, why not put windshield type wiper blades on solar panels? They know dust storms occur frequently. I get this question quite a bit. Why don't they just put windshield wipers on the various Mars rovers that are solar powered? Now, you don't have to worry about Curiosity and Perseverance. They're both powered by nuclear RTGs, nuclear batteries. So they don't have any solar panels, so they don't have to worry about this. But for the regular solar powered spacecraft, yeah, the dust is a problem. And originally, when you had Spirit and Opportunity, NASA's plan was the spacecraft were just going to die. They were going to last for 3 months and then they were going to die. And what they found was that the dust started to accumulate on the solar panels and was starting to dim the amount of energy that was coming to them. And then they would have these events where they would be cleaned. And they weren't entirely sure, and they still aren't entirely sure what's going on. The best guess is that you've got dust devils that are flying across and blowing away the dust over top of the rovers. But the problem with the Mars dust is that it's not just the dust falls on the panels, but that the dust is also a little bit has some static electricity. It kind of clings to the panels. And so if you just go and take some kind of windshield wiper mechanism and try to slide it across the panels, you might just be pushing the dust around and not actually cleaning it off. So you need some way to both handle the static charge of the dust, which is electrostatically connected to your panels, and at the same time actually clean it off. And it turns out that whatever is happening with these cleaning events is doing both. It's dusting off the panels and also handling the static charge on them so that it's moving them away. And it seems to happen often enough that it's not really a problem. The rovers are not dying because too much dust is falling on their panels. The rovers are dying because of, mechanically, Spirit died mechanically and Opportunity died because there was this huge dust storm that lasted for too long and it wasn't able to keep itself warm. And in-situ has, I'm not sure if it's gotten fixed, but right now in-situ's got a little bit of dust on its panels. It's having to slow down, but they see dust devils flying around the landscape. And so who knows when its next cleaning event is going to happen and it's back in business. And, having windshield wipers is just another thing that can go wrong, another piece of equipment that you have to maintain. But I wonder if sort of where we're going to get with that. Will they come up with some solution to actually, you can imagine instead, what if they run some charge through the panel that sort of provides the opposite charge and sort of levitates all the dust away from it? That might be the solution to go. So I'm sure, as more rovers and spacecraft are sent to the surface of Mars, they'll figure this out. Christian Lockman, are there still bacteria living on or in the Voyagers? There is almost certainly bacteria on the Voyagers right now. Because the Voyagers were sent into deep space and before a lot of work was being done for planetary protection, I don't think they did any protection. They didn't clean the Voyagers. They didn't need to clean the Voyagers at all because they were never going to be sent crashing into or landing on places that could harbor life. And back in 1977, they weren't as concerned about these issues as they are today. But living? No. There's going to be bacteria that's going to be in a state of hibernation on the surface of the Voyagers. And so you could go and catch a Voyager, take a sample off the surface of the Voyager, bring it back to Earth, warm it up, feed it, and you could probably bring it back to life. Over time, the more years that they spend in deep space getting blasted by radiation, any life on board is eventually going to get killed pretty dead. But it is still kind of a testimony. The classic story is when the Apollo astronauts went to the moon, they brought back a camera system from one of the previous landers that had been on the moon, and there was bacteria that had been sitting out on the surface of the moon for many years, and when they brought it back to Earth, they were able to revive it. And so it shows that Earth bacteria can handle living in deep space for long periods of time. And in fact, there's been some great experiments that are running on the International Space Station right now, where they have these panels that have a bunch of life forms inside of them, and then they expose them to space for years at a time. And so these life forms have to go through radiation and vacuum and cold temperatures and so on and so forth. And they do fine, no problem. Some, as soon as you bring them back to Earth, they just get right back to work. Others are a little staggered. Some, even after going through this process, could live on Mars. We have life forms right now today that can go to space, live in space, or hibernate in space for many years, and then go to Mars and begin, get going again once they're on the surface of Mars. It's kind of amazing how life can find a way. And it shows you how resilient Earth life already is. And it also kind of gives you a sense of how panspermia could happen, that life could shift from world to world earlier on in the history of the solar system. Lord of Entropy. Dark matter as an exotic substance, not flaws in models' measurements, has become viewed as essentially fact by a large part of at least the public-facing science community. Do you agree? If you ask pretty much every astronomer if dark matter is a thing, they will say yes. Many of them have devoted their lives to it. And not only have they devoted their lives to dark matter being a thing, but they have, they map it. They use it as a tool for being able to gravitationally lens objects that are more distant. They have a really firm handle on which galaxies have dark matter in them and which ones don't. They have multiple lines of evidence that dark matter is a thing that exists in the universe. We are way beyond is it a measurement error? Is it a misunderstanding of how the universe is working? And we're well into the really well categorizing what this thing is. But we still haven't gotten to the point that we know what is the underlying cause. What is the mechanism that is creating dark matter? Is it a particle? What kind of particle? What produced the particle? How many particles are there? Where are the particles? Can we find, what do they interact with, not interact with? What is their mass? What's their spin? What's their charge? We don't know all these things. But the question of whether or not dark matter exists is beyond contention at this point in the astronomy community. Now, you're going to have lots of people who are not in the astronomy community who have they just have like a ad hoc, I don't like it. And I think they just don't like the name dark matter. Dark matter. Oh, astronomers are coming up with the name dark matter because they don't know what it is. It's just a terrible name. If we mentioned this several times in the past, that if dark matter had a better name like the neutrino, right? Neutrino is an object. There are countless numbers of them passing through your body right now. They can pass through a light year of lead and be unaffected. They don't interact with matter in pretty much any way, shape, or form. So that's a great example. I mean, dark matter and neutrinos are almost identical in their profiles and how they work, except that dark matter seems to be moving slowly and neutrinos seem to be moving quickly. And because neutrinos move quickly, they seem to be easier to detect. So yeah, I think the astronomy community has really done their homework in demonstrating that dark matter is a thing. And anybody who questions it, I mean, not questions, it's not like it's a religious thing that, you're an apostate if you question the existence of dark matter. You just have a lot of hurdles to explain. You've got a lot of observations that have been made that can only be explained if there is this invisible matter out there. And not only is anyone free to do so, but there are Nobel Prizes awaiting you if you can do it. And that's always just the way science works. Something is discovered, Some observation is made. Someone says, that's weird. And then other people, I wonder what's going on there. And then they develop hypotheses, and then they attempt to prove themselves wrong. And the longer they go, not being able to prove themselves wrong, the evidence seems to be that that thing is there. And so yeah, it's like, clearly it gets under my skin that people have this, I don't know, just this sort of, I don't like it response to dark matter without really respecting the amount of work that scientists have gone to find it, to tease out its characteristics, and to develop really clever instruments and observations and experiments to try to find it. It's one of the most exciting fields that's out there, because you've got something that you know is there, but not knowing what it is sort of still to be discovered. And so I think it's great. I love it. Horizon Brave. Fraser, do you think bias confirmation exists in the scientific community? Sure. Scientists are human beings, and all human beings have biases that are part of who we are. It's part of our operating system. We all have them all the time. And the magic is when you first learn that you even have these biases. There's a great list. I've seen some posters where they list out all of the cognitive biases that we can be affected by at all times. And even if you know them, and even if you refer to the cognitive biases, you still fall for them because they are just part of your mind's operating system. And we see this all the time. And so because scientists are human beings, you'd expect them to be operating with biases as well. That said, of all of the methods of gaining knowledge that humanity has come up with, the one that is most resilient to bias is the scientific method. Because done well, science is about attempting to disprove your hypothesis. Every other field, people are attempting to prove their hypothesis. And science goes the opposite. It goes, here's an idea, now let me try to find out why it's wrong. And you try and you try and you try. And the longer you go without being able to prove that you're wrong, the more successful the theory probably is. And then someone else can come along and show that you were wrong, and you immediately reject your hypothesis and start again. And it's brutal, and it's humbling, and it is grinding. And it can be really hard on your psyche to be able to go through this process. And yet it is productive. We've gotten where we've gotten because the scientific method at the heart of it, not the people who are trying to implement the scientific method, but the scientific method itself is so resilient and so successful that it has showered us with developments and advances, and will do so in the future. I mean, humanity's course changed utterly during the Renaissance, really when the scientific method was adopted as a way of gaining knowledge. And hopefully it will continue on into the future. And hopefully we'll be able to identify our biases, remove them, counter them, develop procedures to minimize their impact on the work, and science will just get better and better. If you want a single comprehensive resource for space news, then you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights about the story, and links you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to everyone watching here and on Twitch, and to everyone who asked a question. And if you want to ask a question for an upcoming show, you can post it in the YouTube comments or in Patreon, or you can join me live on my YouTube channel every Monday at 5 p.m. Pacific time. Thanks to all the moderators, and a special thanks, as always, to Chad Weber, Nancy Graziano.